Today we're going to pull back the curtain on Apache Kafka, not just what it is, but how it actually works under the hood. By the end of this session, you'll understand why it's become the backbone of event-driven architectures at companies like LinkedIn, Uber, and Airbnb. And more importantly, you'll know exactly how to reason about it when you're designing or debugging your own systems. Kafka started as an internal project at LinkedIn in 2010. They needed something that could handle hundreds of millions of events per day without falling over. The insight was simple but powerful. Treat your data stream like a log, not a queue. That shift in mental model is what separates Kafka from traditional brokers like RabbitMQ. A queue deletes a message once it's consumed. A log keeps it. That means you can replay, reprocess, and fan out to as many consumers as you want, all from the same durable record. Before we go deep, let's get the vocabulary locked in, because Kafka has a very precise model, and mixing up these terms causes real confusion. A topic is your named channel. A partition is how that channel gets split for parallelism. An offset is the address of a specific message within a partition. Think of it as a line number in a file. A broker is a server. A producer writes, a consumer reads, and a consumer group is how you scale readers horizontally without duplicating work. Here's the core mechanic. When you publish a message with a key, Kafka runs that key through a hash function, takes the result modulo the number of partitions, and that determines exactly which partition the message lands in. Every time, so all events for user 42 always go to the same partition, always in order. That's your ordering guarantee, but notice it's scoped to a partition, not the whole topic. If you need global ordering, you need one partition, and that means no parallelism. That trade-off is almost always the wrong call. A Kafka cluster is just a group of brokers, servers that store partition data. For each partition, one broker is elected leader and handles all reads and writes. The other brokers that hold copies are followers. They exist purely to replicate data and take over if the leader goes down. The in-sync replica set, or ISR, is the list of followers that are caught up. If the leader fails, Kafka elects a new leader from that ISR. With a replication factor of 3, you can lose 2 brokers and still not lose a single message. This is where Kafka's power really shows. A consumer group is a team of consumers working together to read a topic. Kafka guarantees that each partition is owned by exactly one member of the group at a time, so you get parallel processing with no duplicate work. Now here's the key. 2 different groups are completely independent. Group A and Group B both get every single message. They each have their own cursor into the log. That's how you fan out the same event stream to an analytics service, a notification service, and an audit service simultaneously, all decoupled from each other. The rebalancing mechanism is what makes scaling seamless. Add an instance, Kafka automatically redistributes the partitions. The offset is just a number, but it's the number that makes Kafka reliable. Every consumer group tracks its own committed offset per partition. That's your resumption point after a crash. Now you have 3 delivery modes to choose from. At most, once commits before processing. Fast, but you lose a message if you crash mid-handler. At least once commits after, you might process the same message twice on a crash, but you never lose one. Exactly. Once requires Kafka transactions and idempotent producers. It's the strongest guarantee, but it adds overhead. For most applications, at least once with an idempotent handler is the practical sweet spot. Let's make this concrete with a real scenario. One producer publishing to a topic with 5 partitions. 2 completely independent services consuming from it. Service Alpha has 2 instances. They split the 5 partitions between them, 3 and 2. Service Beta has 6 instances. 5 get 1 partition each, and the 6th sits idle because there are no partitions left to assign. Both groups receive every message independently. The producer doesn't know or care how many consumers there are. It just fires events into the topic, and Kafka handles the rest. Let's look at what Kafka's range assigner actually does with these numbers. 5 partitions, 2 consumers in Group A. You can't divide evenly, so the first consumer gets 3, and the second gets 2. That's a slight load imbalance, but it's by design. Group B is the more instructive case. 6 consumers competing for 5 partitions. 1 consumer will always sit idle. It's not an error, it's not wasted resources in the network sense, but it is wasted capacity. The lesson here is that your maximum useful parallelism is bounded by your partition count. Adding more consumer instances beyond that gives you exactly 0 throughput gain. What it does give you is a hot standby that can take over instantly if one of the active consumers dies. This is the slide I'd call the "don't do it lightly" slide. Kafka lets you increase partition count at any time, but you cannot decrease it. Ever. And the consequences ripple through your entire system. The most dangerous one is key ordering. Your hash routing is always modulo n. The moment n changes, every key potentially ends up on a different partition. A user's events that were cleanly ordered on P2 are now split. Some historical messages on the old partition, new messages on a new one. Your consumer sees them interleaved. Beyond that, every consumer group triggers a full rebalance, A processing pause, the instant the count changes. Stateful stream processors like Kafka streams may need to fully rebuild their state stores. The right mental model is, partitions are not something you tune dynamically. They're infrastructure decisions you make once, upfront, with a generous buffer for future growth. Let me leave you with the 6 things that should stick. Partitions are your parallelism lever. Set them generously before you go to production. Consumer groups are independent. Use that to fan out events across services for free. Keys are your ordering contract. Same key, same partition, always. More consumers than partitions is just idle capacity. Match them. Offsets are your safety net. They let you replay history and recover from crashes without data loss. And replication is your durability guarantee. 3 copies means you can lose 2 brokers and still not lose a byte. Get these 6 right, and Kafka becomes predictable. Get them wrong, and you'll be debugging ordering issues at 2 a.m.